Welcome to this video where we'll be talking about the accuracy of numerical solutions for ordinary differential equations. So by the end of this video, you will be able to ensure that your numerical ODE solution is accurate. Now, that's really the major question, right? Can we ensure that our numerical solution to the ODE is accurate without even knowing the true solution? Now, for the sake of arguments, let's assume that round-off errors are negligible and therefore that truncation error dominates. And for most engineering applications, that's actually the case if we do our computations in double precision numbers. If we resort to single precision or even half precision numbers, then that statement is not necessarily true. But MATLAB uses by default double precision numbers, and with double precision numbers, it's usually not the round-off error that we need to worry about. The truncation error is usually orders of magnitudes larger. So, what do we know of an ODE solution method concerning its error? Well, we don't know really the error itself, because that would require us to know the true solution. But we know something else about the solution method and the error, and that is the order of the method. So what does that mean? Well, that means that the truncation error is proportional to the order p of the method. Well, strictly speaking, it's proportional to the step size to the power p, the order of the method. So I can write that the true solution is equal to the numerical solution at a given step size h, right, plus the error. But the error is some unknown coefficient a times step size h to the power p, where p is the order of the method. Now, if we let the step size h go to 0, then the numerical solution will be the true solution. And remember, I kind of discarded any round-off errors. In reality, of course, if we really could let h go to 0, then at some point our solution will be dominated by round-off errors instead of truncation errors, and we will actually not recover the true solution, unfortunately. But since we discarded round-off errors, this statement in theory would hold true. So let me write this. So my true solution would be equal to my numerical solution if my step size, and let me just call this h prime for a second here, would go to 0. Okay, up to round-off errors, that would be a true statement. So now let me add a lot of zeros to this equation. I'm going to add the numerical solution that has twice that step size, so 2h squared, and I'm going to subtract that value as well. So I'm just adding 0 here to the right-hand side, and I keep on doing this. I'm going to add and subtract the numerical solution that I'm going to obtain with a step size of twice larger, 4h prime. I'm going to keep on doing this, always adding, subtracting the same value until I add and subtract a numerical solution y that I have obtained with a step size of h divided by 4. I'm going to add and subtract the numerical solution that I will obtain with a step size of h over 2. And then finally, I'm going to add and subtract a numerical solution that I obtain with a step size of h. Okay? Now let me introduce some parentheses in this equation. I'm going to put some parentheses there, over there at the right, and then finally over there. So what do I know about these terms? Well, let me rewrite this equation. The true solution is equal to, well, let me start from the right, is equal to my numerical solution obtained with a step size of h plus, well, this difference. The difference of the numerical solution with a twice finer step size, so a factor of 2 smaller step size, minus my original solution at a step size of h. Well, let me call this the change of my numerical solution when I go from h to h over 2. In some sense, this is the estimated error, right? It's the improvement of my solution when I go from a step size of h to a step size of a factor 2 smaller, h over 2. This next parenthesis then is the change of my numerical solution when I go from a step size of h over 2 to h over 4. And I can keep on going, right? Each combined term, the next one would be the change of the numerical solution when I go from a step size of h over 4 to h over 8, and so on, all the way, right? I have basically infinitely many terms, right? Because I need the h to go to 0. Now, what do I know about these differences, which are essentially estimated errors? Well, if I have a pth order method, I know that errors should decrease by a factor of 2 to the power p, right? And these differences in the simulations, that they are kind of the stand-in, they are the true estimate. They're not the true estimated error, they're the estimated error. So let me rewrite this then. Let me calculate what the error would be. Well, the error is true solution minus the numerical solution at a mesh spacing of h. So if I use that equation up here, right, I have true solution. If I subtract from both sides the numerical solution with a step size of h, I get that's equal to delta, the change, the estimated error, if I go from a solution with a step size of h to a solution with a factor 2 smaller step size, i.e. h over 2. Let me pull this out, and so this gets multiplied by 1. Now I have to add the change of the solution if I go from h over 2 to h over 4. But this estimated error, because it uses a factor 2 smaller meshes, I know should be a factor 2 to the power p smaller than the change that I had going from a step size of h to h over 2. So that should be 1 plus 1 divided by 2 to the power p. And if I go one mesh factor 2 smaller even, one step size factor 2 smaller, I should say, then I have this change from the simulations using a step size of h over 4, changing it to h over 8. And I know that this should be a factor 2 to the power p times 2 to the power p smaller than the original change that I had from going from h to h over 2. So that is 1 divided by 2 to the power p squared. And I keep on going because I know that each one of these estimated errors, these delta y's, should be smaller than the prior one by a factor of 1 divided by 2 to the power p. Right? That should be the smaller factor. So the next one would be 1 divided by 2 to the power p times 1 divided by 2 to the power p squared, which gives me 1 divided by 2 to the power p, entire thing cubed, plus infinitely many terms. So let me write this a little bit more compact. So I have this change in the simulation results going from step size h to h over 2 times, well, I have these infinitely many terms here that I can write as the sum from k equal to 0 to infinity of what? Well, of 1 divided by 2 to the power p, the entire thing to the power k. Okay, so what does that give me? It tells me that the error is equal to this change in the simulation from h to h over 2 times this sum from k equal to 0 to infinity. And that's actually a geometric series that I can calculate what that infinite sum is. It is simply 2 to the power p divided by 2 to the power p minus 1. That's the sum of all of these infinitely many terms. Now, there's one little issue with this formula, because this equation tells me the error for my simulation with a step size of h. But in order to use this formula, I need to calculate this delta, the change if I go from h to h over 2. So I actually need to do a calculation with a factor 2 smaller step size than h, so with a step size of h over 2. And right, so I would have already a better simulation. So let's change this a little bit. I'm just going to copy this equation down. I haven't changed anything yet. And now I am going to multiply this equation by 1. Well, not quite 1. I'm going to multiply it by the change that I get in the numerical simulation from 2h to h. And then I'm going to divide by that very value again. So divide by delta y if I go from 2h to h. So I've just multiplied this equation by 1. So what do I have? Well, let me move that change in the numerical simulation over. So delta from 2h to h times, well, here is the ratio. How much did my estimated error change if I went from h to h over 2 compared to 2h going to h? Well, I know that this has to be similar to 1 divided by 2 to the power p for a pth order method. And then I have the rest of the equation, 2 to the power p divided by 2 to the power p minus 1. And you'll see that the 2 to the power p is in the numerator and the denominator, so that cancels each other out, which means that the error, if I calculate numerical solutions for a step size of 2h and h, take their difference, times 1 divided by 2 to the power p minus 1 gives me the error of the simulation with a step size of h. So with this equation, I don't have to do another simulation with a step size half of h. Okay, so here's then the strategy for a pth order method to find the solution within a certain threshold. Let's call that threshold EOK of the unknown true solution. All right? While my estimate here for the error, which is the change from a simulation with 2h to h times 1 divided by 2 to the power p minus 1, is greater than my OK error, EOK, then do this. Half the step size, so set the new h to h over 2. Recalculate the ODE solution from scratch, starting with the initial constraint, with the constraint that's given in the problem, and find a new numerical solution with that new step size h. With that new solution, you can calculate the change in the numerical solution from 2h to h if you stored the prior result. And I'm just going to take the absolute values of this. And then we can calculate the new error in the while statement. And we keep on going until this statement of the change in y values times 1 divided by 2 to the power p minus 1 is no longer greater than our acceptable threshold. Now, there is a prerequisite for this procedure to work, right? And it is inherently baked into the formula that we're using, namely that successive changes of this delta y should reduce by roughly 1 divided by 2 to the power p. Now, in order for us to check this, we need to perform at least 3 simulations, reducing h by a factor of 2 for each one of these simulations. Why? Right? We need 2 delta y's, and each delta y uses 2 simulations, and one of them is reused. So we need a total of 3 simulations to check this. Now we can check this in the while loop above, right? We could just print out to screen what the successive ratios, the reduction of these delta y's is, and check whether that is close to 1 divided by 2 to the power p, or we can look at the reciprocal value, which is oftentimes easier to look at, to check whether that reciprocal ratio of the delta y's is close to 2 to the power p, where p is the order of the method. Now, there's one observation that I want to make here concerning which order of method should we really choose. And you'll see from this formula up here that the higher the order p is, the faster the above while loop will be done, because this e on the left-hand side here reduces quicker. Now, why is that? Well, the higher the p, the faster the delta y's are reduced, right? Because they get reduced by a factor of 2 to the power p. And the higher the p, the smaller that ratio is, 1 divided by 2 to the power p minus 1, right? So higher order p methods would converge this faster, this while loop, make it true faster. But of course, the higher the order p is, the more storage and calculations per step are required. But typically that does not outweigh the benefits that we get by being able to converge the while loop faster. So that's why typically higher order methods are preferable over lower order methods, meaning just first or second order methods, and we tend to want to use third or fourth order methods. Okay, so here's a challenge question using the application of this. And in the top right here is the equation from the previous slide. So here's the challenge. The height h of water at t equal to 60 seconds in a tank is calculated solving an ODE using the first order RK1 method, right? And what's the ODE? Well, in the overview to this module 8, we looked at the ODE that describes the height of water in a tank. So we're solving this ODE with a first order RK1 method. So forward Euler, basically. Now, to determine the height h to within at least 1 millimeter of the unknown true solution to the ODE, up to which step size, delta t, must we perform calculations? So here's a table of just a series of calculations that were performed. And for each simulation that we perform, after that we perform another simulation, reducing the step size delta t by another factor of 2. So we go from delta t of 1, 0.5, 0.25, 0.125, and so on. And we'll get different answers for our height, in this case here in millimeters, for the height of water in the tank after 60 seconds. Then shown here in this table in the fourth column is the change in heights from one simulation to the prior simulation. So that would correspond to the formula that we had, the delta y, if we go from 2h to h. And then also shown in the last column is the inverse of the ratio of these delta h's, these delta y's. So the question is, if we look at this data table, at what delta t could we have stopped the while loop, because the answer that we then obtain is within at least 1 millimeter of the unknown true solutions. And the options that you have are for A, delta t equal to 0.5, so the second row data, delta t equal to 0.25, the third row data. Option C, delta t factor 2 smaller, 0.125. And option D is, well, we'll have to do simulations less than or equal to 0.0625. Or your option E is, well, no idea, because we don't really know the exact solution. So how are we going to know whether we're within 1 millimeter of an unknown true solution? Please make your choice. Okay, so the correct answer here would be that we have to perform calculations up to a delta t of 0.25. Now, why is that? Well, let's apply the formula that we derived previously. This E value would be the change that we obtain when we run at a simulation of step size 0.25 compared to the prior step size of 0.5. And that change here is given in the table as 0.585 millimeters. And then we have to multiply this by 1 divided by 2 to the power p minus 1. And we have a first order method, so the p is equal to 1. So we have to multiply this by 1 divided by 2 to the power 1 is 2, minus 1 is 1. So we multiply the 0.585 millimeters by 1. And so the E is equal to 0.585 millimeters. But we want to know our answer up to at least 1 millimeter, which means our EOK value is 1 millimeter. And 0.585 millimeters is smaller or equal to 1 millimeter. So that means we have satisfied the condition of our while loop and we can stop the simulations. Now, if we do this kind of analysis, we have to check whether our changes in the numerical results actually reduce with 2 to the power p. So that's what's shown here in the last column here. Those ratios should be close to 2 to the power 1 should be close to 2. And you'll see that these values are, well, they are pretty close to 2, acceptably close to 2. 2.275 seems not that close to 2 actually. So if we would be worried a little bit of this not being close enough to 2, we would perform another simulation at 0.125 and we'll see that this ratio actually approaches 2 in the end. So the error, the change reduces according to the formula that we have used. Thank you for watching.